I'm Derek from the Nerds 4.0 at Stonehill Middle School. Today I'm going to be testing our wind turbine, the wind tower. This is the wind turbine out of water. This below here would be underwater. These are leg weight packs that this is 5 pounds worth of weight distributed evenly, so it pulls it straight down. Because if we had it to one side, it would lean. It would probably lean in the water a little bit, because this isn't airtight completely, because again, it is just plastic sealed with duct tape and glue, Gorilla Glue. So I'll take these off. And this is it, how it would be in real life, except for the materials. These are the propeller blades, the rotor blades that turn a shaft that it leads to a generator inside of this block right here, which is the actual wind turbine part, like engine of the whole entire thing, that would generate electricity. This is the tail that leads to the tail fin that lets it turn when wind hits it from the side. This block right here is the above water shock absorber. So it helps when it's swaying to a side. There's springs connected to a concrete block that will push that concrete block back, throwing it weight. Because let's say I'm tipping over like this. If I were to be holding a 10-pound weight in my hand, and if I had the strength to go like this, I would come back this way. It works just like that. This is the tower. Holds up this and connects it to the rest of it. It's bigger at the bottom than the top because we want it to be smaller. Because the smaller, the less wind that can touch it. But to deal with the wind that does touch it, there's grooves up the sides of it that direct the wind up and over and out of the way, so they won't push the tower over. Because if we did it, the tower would just be like this, whatever direction the wind's coming. This is the flotation device. This device keeps it up because this is all weight. This is all just meant to pull this tower down so it doesn't just fall over like this. Because if this was sealed but it was all air, well, that's why we drill these holes, so that water could get in so it could fall down. Because if it was all air, it would just completely fall over and it wouldn't go below like about here, because this is all just air. This piece is purely just because we had to seal this off so that this could get connected to it. These two blocks right here. There's a block right here if you can't see it. This block is the below water shock absorber. It does the exact opposite of what this is doing in like the direction. They have the same exact function, but if, let's say this block, this spring right here is contracted, the opposite block, this string is like that, springs like that. And so then they'll get like that, and then they'll get pushed back and forth until they align again. And this is the bottom counterweight. In real life, there would be spikes, 4 spikes, to cut through the water's currents. But we tried to create that out of styrofoam, but that didn't work out too well. So that is just purely to pull it down. We had to make it out of wood since we don't have any other material that we can really model and fit to our likings. And wood kind of floats, so it kind of does the opposite of what our actual counterweight would actually do. But it's just a model. The duct tape is just to seal it off and make sure it stays together. The cardboard right here does the same thing as the block of wood down there. We did this thin piece of wood because this needs to connect to this. We did wood down here and cardboard up here because the cardboard would just fall apart if it was down there, and the cardboard up here, it's not going to be touching any water, so it's fine. I'm going to test its floatability. This is a 1 centimeter to 300 centimeter scale, so this 300 times would be how big the actual thing would be. We drilled these holes in it, one here, one there, one there, and one there, to make sure it fills up, because on an actual wind tower, it would be filled with concrete. So right now we have to let it fill up. We had to strap 5 pounds worth of weight to the bottom of this tower, the white PVC pipe you see here, to compensate for the lack of concrete that would be there in real life, because it won't go all the way down because water weighs just as much as water. So here it is. It floats. A problem we encountered is that these two frisbees aren't completely airtight, so you can see it is sinking a little. So this works how, so this would be sitting in the water, and since the most powerful wind happens in the water, these would spin, generating electricity in the wind turbine. Now what we also incorporated, because modern wind turbines only face one direction, this spins like a weather vane. So if wind was coming, let's say it was coming this way and this was spinning, and then the wind changed direction and started coming from this way, this tail right here would pull it around like this so that it can catch 100% of the wind. This part right here is the flotation device. It works. See, it would sink to the bottom if it weren't for this device right here. Now it's not working 100% because it is just two frisbees glued and duct taped together, because we don't have the greatest model abilities. This is the above water tower. This supports this. It's thicker at the bottom than it is up here. On the actual thing, there is the grooves that would go around, like in the Chicago Spire, which you can read in that PowerPoint. There's a counterweight block and a shock absorber block on the bottom. The counterweight pulls it down. It kind of didn't work out too well in the model because it's made of wood and wood floats. And the shock absorber is a block suspended by four springs on either side. 1, 2, 3, 4. So if it were to go, let's say, it were to push this way, the spring would retract and then push out to fling it back to the upright position. What else? In choppy waters, it stays upright because of the flotation device. The flotation device counters it out, and it would even more in the shock absorber. High winds would be deflected off of the grooves off the side, because how it works, if you didn't see the PowerPoint, is the grooves go like this, and the wind would hit this and just get deflected up and around. It wouldn't interfere with the propellers at all. What else? Okay, after observing our model and how it did in a real life test, the first thing we do was not make it out of wood, which we would do in real life. It'd obviously be concrete and steel, galvanized steel, so it wouldn't rust. We'd make the flotation device larger because it's a decent size right now, and obviously it would be airtight in real life, but we would definitely make it larger to increase the surface area that is touching the water, so it would make it much more stable. The rest of it turned out exactly how we hoped it would, and it works to our standards. The Nerds 4.0 from Stonehill, thank you for watching our video presentation.